Let's suppose we've got two composable linear maps, S and T. So here in my picture, I've got S as being a linear map from a vector space U to a vector space V, and T being a linear map from V to another vector space W. Well, their composition, T composed with S, is a function from U to W, and in fact, T composed with S is again a linear map. I'm just going to check part of the definition so you can see that this really is an easy fact about linear maps. If you take X and Y to be elements of U, then if you look at T composed with S of X plus Y, that means T of S of X plus Y, but because S is a linear map, I can rewrite this as T of S of X plus S of Y, and because T is a linear map, this is T of S of X plus T of S of Y, which is T composed with S applied to X plus T composed with S applied to Y. Now, if you want to complete the proof that T composed with S is linear, you need to check that T composed with S has the linearity property to do with scalar multiples. It's just as easy as that was to do, so I'm going to leave that to you. In any event, now we know that if two composable maps are linear, then their composition is linear as well. So let's suppose we have some bases for our vector spaces U, V, and W. We'll take a basis B for U, C for V, and D for W. We can then start thinking about matrices of linear maps. And we can ask the question, how is the matrix of T composed with S with respect to the initial basis B and the final basis D related to the matrix of T with respect to initial basis C and final basis D, and the matrix of S with respect to initial basis B and final basis C? Well, of course, the answer is that you get the matrix for T composed with S by multiplying together the matrix for T and the matrix for S. And that's the theorem which we're going to prove during the rest of this video. Here's the formal statement of what we're going to prove, and it uses exactly the same notation and setup as on the previous slide. We take S to be a linear map from U to V, T to be a linear map from V to W, and we choose bases B, C, and D for the vector spaces U, V, and W respectively. Then what the theorem claims is that the matrix of T composed with S with respect to initial basis B and final basis D is equal to the matrix product of the matrix of T with respect to initial basis C and final basis D, and the matrix of S with respect to initial basis B and final basis C. So what this theorem does is actually give some justification to our definition of matrix multiplication. The definition of matrix multiplication sometimes seems quite unnatural when you first meet it, but in fact this theorem is telling you that our definition of matrix multiplication is a sensible one because it corresponds to composition of linear maps in the sense of this theorem. So to prove this, we're going to set up some definitions and notation on this slide, and then we're going to continue the proof on the next slide. And I've reminded you at the bottom of the slide of the definition of the matrix with a linear map with respect to a given initial and final basis. So we're going to have some notation for the matrix of T and the matrix of S as they're written here. So what we will do is we will write the matrix of T with respect to the initial basis C and the final basis D be the matrix whose ij entry is written as lowercase t subscript ij. And you'll recall, or you can just look at the definition at the bottom of the screen if you want, that what that means is that if you take T and you evaluate it at any one of the basis vectors Cj coming from the basis C of V, then that is equal to the sum from, in this case, I equals 1 to n of t I j times d j. Excuse me, di. We're also going to have some notation for the matrix of S. So we will let the matrix of S with respect to the initial basis B and final basis C have ij entry lowercase s ij, and again what that means is that if you take S and you evaluate it at any of the basis elements B subscript j, then that is equal to the sum from dummy variable I equals 1 up to m of s ij times the basis element cj. What we need to prove now is that the matrix of T composed with S, with respect to initial basis B and final basis D, is the same as the ij entry that you get when you multiply together the matrix for T and the matrix for S. So what is that ij entry of T composed with S, the matrix of T composed with S with respect to initial basis B and final basis D? The ij entry of T composed with S with respect to initial basis B and final basis D is the coefficient of di in T composed with S applied to Bj. In other words, what you have to do to find the ij entry of that matrix is to compute T composed with S at the jth basis element of B, which is B sub j, express that as a linear combination of the d's, and then the coefficient of di is the ij entry in T composed in the matrix of T composed with S with respect to initial basis B and final basis D. That's what the definition of the matrix of a linear map says. So what we have to do is we have to compute this in other words, work out T composed with S evaluated at Bj as a linear combination of the d's and show that it equals the ij entry of the matrix of T multiplied by the matrix of S. Okay, so that's what we need to do in order to prove this theorem. So we're now going to do it. So we have to work out T composed with S at the jth basis element Bj from our basis B of the vector space U. So of course what this means is T of S of B subscript j and we know how to express S of B subscript j in terms of the basis C, because we introduced some notation for the matrix of S. And the notation that we used meant that S of Bj was equal to the sum from I equals 1 up to m of, actually I'm going to use a different dummy variable. I'm going to use k. K equals 1 up to m of S kj times C k. So that is simply the definition of the matrix of S with respect to initial basis B and final basis C. Now we're applying a linear map T to a sum. So because T is linear, I can rewrite this as the sum from k equals 1 up to m of skj. Remember, the skj's are just scalars, they're just elements of the field over which our vector spaces are fields. So I get this. Okay, again, we know the matrix of T with respect to the initial basis C and the final basis D. We had some notation for that, and that notation allows us to expand T of CK. So this is what we get. Now we can manipulate this sum a little bit. So let's rewrite it as the sum from k equals 1 to m of the sum from I equals 1 to n of s k j t I k d I, just multiplying this scalar into the following sum. So what we wanted was the coefficient of di, because the coefficient of di was going to be the ij entry of the matrix of Ts. So let's collect together all the terms in di. We can do that by swapping the order of summation. So we can rewrite this, if we want, with the I summation first. So because we have a sum of finitely many terms, it doesn't matter what order we add them up in, so we can swap the order of summation. When we do that, we get the same thing, tik times skj times di. And I'm going to bracket this in a particular way so that we can see what the coefficient of di is. This stuff in the middle doesn't involve, this stuff in the middle is then the coefficient of di. Sum from k equals 1 to m t I k times s k j. You should recognize that as the formula that's used when you compute the product of two matrices. Okay, we have computed the ij entry of the matrix of T composed with S, and we found that it's the same as the ij entry of the matrix product of the matrix of T times the matrix product of S. Therefore, the matrix of T composed with S is equal to the matrix product of the matrix of T and the matrix of S. That was what we wanted to prove. So we're done with our theorem. If you're concerned whether these matrices have the same size or not, well, you can check nice and easily that they really do. For the matrix of T would have n rows and m columns, and the matrix of S would have M rows and L columns, so their product really would have the correct size, which is n by L, to be the matrix of S composed with T. Sorry, T composed with S.